Procedural generation is a method that is used by many games to create expansive worlds with unique details that could not otherwise be created by hand. It's used in many popular games such as Minecraft, and is an effective tool used in crafting unique player experiences every time you generate a new world. In this video, I will be explaining my implementation of procedural generation, which uses a rule tiling system to create environments out of pre-made tiles, inspired by Animal Crossing: New Horizons. This project was made in Unity for a university assignment. Like many other procedural world generators, I use noise to instruct where the tiles should go. Going back to my first attempt, we can see that in action, a tile is instantiated wherever the noise is above a certain threshold. Obviously, this isn't the most performant solution though. For the noise, I leverage a library called Fast Noise Light, which has many useful features for generating different types of noise. For my terrain, I decided to go with simplex noise, as it seems to give the best results. In Unity, I've wrapped the noise generators in scriptable objects, which makes them easier to manage and can even be changed while the game is running and have their data be saved. Going forward a bit, I've improved the world rendering by splitting the terrain up into more manageable chunks. By building lists of all the tiles, I was able to separate them out into identical meshes and draw them as batches using Unity's graphics library. Although this is not the method I ended up going with, it's still much faster than instantiating them all as separate game objects. More importantly, you can see the rule tiling system in use, which checks against adjacent tiles to figure out what mesh the tile should use. As you can see, the edges and corners are a separate mesh, however it does not work between chunks at this time. In my eyes, the benefit of creating a world this way over an established method, like creating cubic meshes like in Minecraft, is that I believe that the blocky terrain backs the art into a corner where everything needs to be blocky just to match. Alternatively, Animal Crossing maintains the blocky tiling terrain while having organic shapes needed to be compatible with other art styles. Going further, I added support for multiple levels of terrain, as well as new tiles that complete the look. In addition, I added a cursor that lets tiles be placed on the terrain, so as you can see, it updates in real time as I click. The new tiles automatically solve to the correct shapes. In addition, you can see that the tiles now sample adjacent chunks, so that tiles are shaped correctly on chunk boundaries. I'd also like to talk about multi-threading, which is used to generate multiple chunks at the same time. For my project, I use a library called Unitask, which has many helpful features to improve the experience using threads as well as asynchronous operations. My world generation script runs the chunk generation methods from the thread pool, which allows multiple threads of the CPU to generate chunks rather than just using the one main thread. This greatly speeds up the generation of chunk data and frees up the main thread to handle other things, keeping the game running smoothly. However, Unity's API is not thread safe, so anything performed on it needs to be passed back to the main thread. For this, I use concurrent queues to buffer information, such as saying, hey, this chunk is ready, from the generation threads back to the main thread. I've also changed the rendering so that per chunk, the tiles are combined into one mesh per material, which are drawn using Unity's rendering library. Doing it this way greatly reduces the lag from rendering, and it makes it possible to generate things such as colliders so that the player can interact with the world. The meshes are only ever updated when the chunk is generated and when a tile is changed, and only the material that those tiles belong to will have their meshes updated. This reduces the overall amount of times that a chunk mesh needs to be regenerated. Something that came up while working with the generated meshes is that they were not being properly released from memory, resulting in a memory leak. This is because meshes are not handled the same as other data. Once you're done with them, it is important to manually release them from memory. As the mesh generation relies heavily on the Unity API, this cannot be done using multi-threading. Reworking this in the future to use custom implementations more tailored to my use case that could take advantage of multi-threading would benefit the performance massively. Moving forward through the project's progress again, it's really starting to take shape. The terrain is now textured and we can see the emergence of the terrain feature system. Let's talk about the terrain tiles for a bit to see how they work to create the terrain mesh. The terrain pieces only consist of 7 unique parts. The edges and corners can be rotated to create the variants needed to put together the terrain. There are also cliff variants that are used later on to get rid of the seams between vertically stacked tiles. Switching to vertex color view, we can see where the grass and dirt textures are defined using a shader in Unity. Although this works well, the transition is a bit sharp, and I would like to take this further to get a more organic transition in the future. All the assets produced for this project were made in the open source 3D software Blender. The tile's final data, which describes its appearance, location, and rotation, is retrieved by using my rule tile solution, which gathers information about surrounding tiles and compares them to rules that I've defined. This solution was inspired by Unity's very own implementation of 2D rule tiles. These rules can even be set to rotational, which checks all 4 possible directions, alleviating the need to make a tile for each rotation. The tile's rotation is stored as a single byte to save on memory, which can be converted into a quaternion for matrix calculations. As well as this, the tile's location is stored as only 3 bytes as opposed to a vector3 int. It uses 4 times less memory to do so. I can do this because the tile's location only needs to be stored within the 16 by 16 chunk size. The global position can be inferred by using the chunk's location. Inside the chunk, the tiles are stored in a predefined 3D array, storing tiles inside the chunk bounds, which is currently a 16 by 16 square with a max height of 10 tiles. Originally, this was a dictionary, however I decided to change it to an array to reduce the amount of memory allocations needed when expanding the dictionaries, and this produced lag. As the arrays take up a predefined amount of space, they are much faster to change if you know the address. However, the chunks themselves are stored in a dictionary. I ended up going with this because it makes it easier to handle chunks in negative coordinates, and expanding and shrinking the array seemed inefficient, as well as the fact I would have had to load each chunk into memory inside the bounds even if the player wasn't in them. But it's not just any dictionary, it's a concurrent dictionary, which is special because they are designed to handle multiple threads, so it handles the chunk generation threads at the same time. I have read into octrees, which could be a way of storing information sparsely which would greatly optimize both the chunk and tile system. This is something I'd like to look into in the future. Moving further along, I've been working on the static entity system for handling things like trees and rocks, which are making the terrain look better already. Let's look at how I've used object pooling to handle the assets on the terrain. By letting the world generate and selecting one of the trees, we can follow it to see how it is being reused by the static entity manager to populate new tree spots. This is an efficient way of reusing assets. Instead of constantly instantiating and destroying game objects, which causes a lot of garbage and lag, the trees are put where they are needed, ready for the player to see. An interesting alternative worth investigating is using Unity's entity component system, which can handle large amounts of data at once, but that's for another project. The static entity manager works like this. When a tile is updated, if it contains the iEntity data interface, this means that it needs a static entity. This tile becomes tracked, and whenever the chunk becomes loaded, it retrieves the appropriate game object from a pool, and whenever it is unloaded or released from memory, the game object is put back into the pool, ready to be reused again. I'd also like to take a moment to talk about these stunning wobbly wavy trees which use vertex colors to cache the pivots of the leaves and wobble them in a very satisfying way, reminiscent of the trees from Animal Crossing. I got this method, coined pivot caching, from the very skilled Martin Donald, who goes into depth about how this method works in his video about the topic. I lovingly ported his implementation from the Godot engine shader language to Unity's shader graph, and there are a few notable changes that I would like to mention. For one, I did not need to convert the vertex colors from sRGB to linear as mentioned in the video, as they already seem to be in the linear color space. This could be due to an update in Blender, meaning linear is now the default. Additionally, both the X and Z coordinates must be inverted to be compatible with Unity's coordinate space. I heavily recommend that you watch Martin's video on this though, as he does an excellent job at describing how it works. I did a lot of work updating the assets for the project to make the world look even more gorgeous, such as creating a high poly leaf to bake as a normal texture in Substance Painter to give the leaves more life. As well as this, I used Substance Painter to create or update the other textures. I even added some new foliage to sprinkle across the terrain, such as grass and bushes. To bring it all together, I implemented a world curving effect that bends the world over the horizon. This is great as it works amazingly to hide the world's generation at long distances and invokes a sense of scale in the world. I'd like to thank the YouTuber NotSlop for his implementation of this effect, which I adjusted to work in all axes, and his method to adjust the camera's frustum so that the curved world is properly culled. A feature that I found that seemed to be quite hidden was creating global shader parameters in Unity Shader Graph. As every material needs to implement the shader that enables world curving, it seemed inefficient to set the parameters for each one manually, as they all needed to be the same. By disabling the expose setting in the parameter, you can use a line of code to globally change any parameter that uses that reference, simplifying adjustments tremendously. I also decided to replace the boring Unity skybox to something much prettier. This skybox is just something I found on the Unity asset store. I would have liked to make my own procedural implementation, but as I didn't have much time left on this project, this would do, and I think it really fits in. But adjustments had to be made to make sure that the skybox would fit into this world. The skybox's horizon by default was in the wrong place due to my curved world. However, with this great skybox shader I found, I was able to offset the skybox and make it look like the clouds stretched on forever. I also added this subtle effect that rotates the skybox slowly, making it look like the wind is blowing in the clouds, which I think makes the leaves look even more authentic. This brings us to the current state of the project. I implemented a starting UI that allows you to generate a world from a specific seed, which can be any string input. The worlds generated from the same seed are always identical. I've created multiple layers of noise generation for the terrain features, such as generating clusters of trees and grass to make the generation feel more organic. I also made improvements to the water shader, which was originally just Voronoi noise. I added some depth to it as well as sparkly flecks to the surface to really make it beautiful. I also created this little gnome guy so the player would have a character to control. I used the existing mesh generation system to generate collision meshes for the world. Making sure to keep performance in mind, I made lower poly variants of the land tiles so that the mesh colliders would not have a very high poly count. Originally, I was just going to leave it at the world generation, but I thought it'd be important to show how the player would move and fit into the world I'm building, so it's easier to imagine the gameplay possibilities. I'm imagining a game that combines life sim and RPG aspects, combining the best of both. Exploring the world, delving dungeons and slaying enemies to build your wealth, so you can come back with supplies to take care of your community and raise a strong society. One game that surprised me with how fun it was Dragon Quest Builders, which combines base defense with exploration and town management. I'd love to capture some of those aspects in this project in the future, as I think it's a very satisfying combination that gives a lot of purpose to the layout and furnishings of the player-made structures, which I really appreciate. Overall, this project is really interesting to work on, and it taught me many key concepts that will surely be useful going forward with this project and others. As my first go at a procedurally generated world using a method which during my research seemed fairly undocumented, I am very happy with the outcome, and I think this world looks great. If I were to continue on this project, I think I could do with a major refactor to improve its optimization, as the mesh generation still seems quite heavy on performance. But I think ironing out these issues and revamping the rule tile feature to make it easier to work with, this would be a great foundation for an interesting take on an open world. If you'd like to check the project out for yourself, as this is an assignment, the GitHub repository will be available in the description, and any comments about how you would improve this method would be greatly appreciated. Thank you for sticking around to hear about this project, and expect more in the future.